Hello and welcome to another installment of Mattia's calculus tutorials. By now you should have thoroughly bathed in the greatness of the ratio test. But like all great things in life, it's not almighty. Sometimes in the ratio test you will get an inconclusive result. But don't fret, there are solutions to the dreaded one. The first of those is the limit comparison test. And the idea behind that is you take a ratio of two functions, one that you already know the one that you already know converges, and one that you do not know, the function in question. And what you basically do is set up a limit as the variable goes to infinity of what you know, of the function over what you know. And basically, you solve the limit, and you'll get a number, or you'll get a solution. And if it's a number between 0 and infinity, they both do the same thing. So if what you know converges, then the function in question will also converge. If what you know diverges, then the function in question will also diverge. Now let's say you do the limit, and you get either 0 or infinity. That means that what you know and the function in question do opposite things. If what you know converges, then the function will diverge. If what you know diverges, then the function in question will converge. The next one of these tests is the direct comparison test. Now, the idea behind this is if you are below a function that converges, then it must converge as well. If you are above a function that diverges, then it must diverge as well. So you must be below a function that diverges, above a function that diverges, or below a function that converges. Now, a simple way to tell is using the p-series test, which basically states that in a summation from some number to infinity, 1 over n to the p, if p is greater than 1, the series converges. If p is less than or equal to 1, it diverges. And you could use these rules back in the limit test to set up functions that you would need to know. So you would use the direct comparison test by setting up a ratio again of the function in question and the function that you know. And basically, if what you know diverges, and you want to be greater than something that diverges, the ratio should be greater than 1. If what you know converges, and you want to be below something that converges, it should be less than 1. Now, the last two tests are even more simple. The integral test, which basically you have a summation, a series of a function. You can turn that into an integral. From the number to infinity. Now, this is an improper integral, so to solve it, you'd have to set it up as a limit. And then you could anti-derive. and eventually you could solve it out. Now, if you can't solve it out, then you know that the original series diverges. If you can solve it, then the original series also converges. Now the last test, the alternating series test, will probably be your favorite. And what that basically states is that if you have a series and it 1 alternates and 2 heads towards 0, then it automatically converges. An example of this would be n equals 1 to infinity of negative 1 to the n over n. So the n, the denominator, takes care of heading towards 0. And the negative 1 that alternates from negative 1 to positive 1 as it goes from even to odd powers takes care of the alternating. Therefore, by the alternating series test, this converges. Now remember, these 4 tests are secondary. You should always turn to the ratio test first. If the ratio test is inconclusive, then you'd either turn to the ratio test, the limit comparison test, the direct comparison test, the integral test, and the alternating series test. Thank you for watching.